what do you think would make it would make the biggest difference, or do you think they would all be equal? Just kind of imagine you're taking like a little weight, you're going to set it on top of the record. You can imagine it's fairly heavy, so that you can really kind of visualize how hard are they going to be for me to try to push that. So imagine I set it in one of these three positions. Will it be equally hard for me to rotate in all those positions?
No.
Do you think?
No.
It'll get more difficult as it goes out.
It's more difficult to go. Why do you think that is?
The center mass is getting pulled away.
The center mass will be farther out.
It's also traveling.
A longer distance.
Okay. Do you have a comment, Cyrus?
Different masses. It would be easier to spin the closer it is to the center, because the mass itself is technically traveling a shorter distance.
Yes, I heard Nick, you just said the same thing, right? Yeah. Talking about the distance. So, if you were to actually ask for these three guys, if I put a mass in each of those places, the angular distance would be the same for all of them, right? But what about the linear distance that they travel, the linear velocity?
Three would be a little higher for 3 than it is for 1.
Yeah, it is higher for 3, right? It's like the farther out you go in the circle, you're traveling on a bigger circle. So each of these guys has a different circle that it's traveling on. And that circle is important because they're traveling faster, right? Each of these guys has its own circle. So it kind of makes sense, right? That so it is true. Your intuition is just right. Kind of the way you're visualizing it. It does get harder to push that when it's farther out. And the reason, as we've said, is that really this guy is being accelerated more. As far as like, if you were to ask what this form of Newton's law says about that, this guy seems like he requires a bigger acceleration. He's sitting at a bigger circle. So it does make sense. We don't really want to use this form of Newton's law because it's not very natural. But the idea that it is a higher acceleration is important. So we want this guy, when we recast this into an angular form, we would like this guy to account for the fact that things that are on bigger circles or that are farther out, they are more difficult to accelerate in an angular sense, right? So that is important. And it turns out, so everything you said so far is right. It turns out that the form of this is dependent on the radius squared. So it's not to the first power, it's actually to the second power. So it does make a big difference on the radius. So if I were to put a mass, if let's say these are 3 equally spaced things, this one's at radius r, 2r, and 3r, this guy being at 3 times the radius of this one, you're actually going to square it. So it's 3 squared, it's like 9 times more of an impact. So it would be like 9 times harder to spin this guy out here than it would be to spin this one. So the radius is actually very important. That's how the contribution is come into play. Okay, so good. This kind of helps us get a little bit towards an angular form. The way that I is going to work is, of course, we usually have more than one thing that's involved here, so we can imagine splitting it up into pieces so that each piece has its own mass and each piece has its own radius. And we're just going to take the mr squared from each piece and just sum those all together. So every piece will just contribute an mr squared to the total. So that's, if you were to imagine something like this, imagine we have 2 masses that are connected by a massless rod unit. They're spinning around this axis, kind of like this. What would be like the equivalent I for that? So I would call the moment of inertia, by the way. I can write that here. That's just the name that we give to it. That resistance to the angular change. So let's say that this guy has a mass m and this guy has a mass 3m. And let's say that this one's length distance away from the axis is L, and this one is is a distance 2L from the axis. So we're just imagining some kind of a rod that has two masses on it. We're going to fix it right here in the middle and just whirl it around. And we're interested, how difficult is it to whirl around? Well, we just look at our thing here that says, okay, I tells us how difficult it is, and every piece contributes mr squared to the total. So what I would do here is I would just say ml squared for this guy, because his distance away from the axis is L, and his mass is m. And then this guy would have a 3m, because he's bigger on this side, and then his radius is 2L, and I'm going to square that. So his contribution, mr squared, looks like this. And then if I put that all together, just multiply it out, then I get 13ml squared for the total. So this is like an example of how you would calculate I, for like a really simple case. So every piece, the take home is, it contributes mr squared to the total, and you see a very simple example of just two pieces together like that. So obviously they're not usually so simple. And this is another really good example of when our calculus will really be helpful for us. Because we can imagine things that are not concentrated at a point. So here we had a very simple case. We had two concentrations of mass that were just at two different positions. I just had to do an mr squared for each one of them. But let's imagine a more difficult case, such as a sphere. So just visualize how difficult would it be to take a spherical object and to spin it around. So it's just a uniformly, just a solid sphere's uniformly distributed mass. Why is this not immediately obvious what the answer is? Marty?
You have to take it and slice it.
It's a different shape.
Put all together.
Yeah, that's the idea. So the point is that we don't have a concentration of mass at a single point, right? So we said that if we had a concentration of mass at a single point, it's just mr squared is what we get from that, right? We can add all those together, but there's no concentration of mass here. And what it means is that we need to try to decompose, we need to try to break it up into pieces still. Why don't we take as an example in this problem, let's say that I told you that I for a disk equals half mr squared, where m is the mass of the disk, and r is the radius of the disk. Let's say that you know that as a given. And that comes from these kinds of things over here. We would like to use this to try to figure out the sphere. What's your question?
Why is there no concentration in mass?
Well, it's just spread out. It's spread out over the entire volume of the sphere. So we can imagine that we have different pieces. It is still true that we have different pieces all over the sphere. Every single piece will contribute mr squared to the total. So the mass that's located at the edges will be more because they're farther out.
Center of mass.
But of course, here we have the same issue. Each one of these pieces contributes mr squared. We have to sum them up somehow. And since the sphere is uniformly distributed, there's not a single place it's concentrated. It's spread out over the entire volume. Why don't we take this as a starting point? Let's say that the moment of inertia for a disk spinning around its center will be half mr squared. All right. So what can I do to actually do this? So what we'd like to go through, this is similar to what we did last time with center of mass. We'll go through it quicker because we have some practice with integration from center of mass, but we're going to do exactly the same thing here, right? And what I want to do is I'd like to decompose this somehow. And how should we decompose it? So I already gave you the answer for a disk, right? So if we could, as y'all said, split it up into a lot of disks, then we could maybe sum all those disks together. Can you visualize a sphere? Is that possible? To imagine a sphere as a combination of a lot of different layers of disks? So that's basically our strategy. What I'm going to do for my integration is I'm going to draw one of the disks just as an example. It's always important to draw an example. So let's just take one here. So here's one of my disks. I'm just put one layer there. It's the center of the sphere. The idea here is, as usual, I'm always going to do this by, this is what I want to know, right? And I'm going to write it like this first. The reason I do that is to be very clear conceptually what I'm trying to do. What we're saying is that the total I for the sphere, of course, will just be the sum of all the contributions of all the disks. And di will represent the contribution from a single disk. Why does it have to be infinitesimal, the disk? Well, why don't I just build a sphere out of like 4 disks?
It's not as accurate as speed. It'll just be like.
That doesn't reflect the curvature.
Approximation.
Yeah, it's not gonna curve like a sphere does. It would be like a stair step, and I don't want this. That's not exactly a sphere. But if I make them very, very, very thin, then I can basically approximate a sphere perfectly, right? So that means every time I take a larger disk, I'm going to get a stair-step pattern. It won't exactly be the curve, but if I take an infinite number of such disks that are infinitesimally thin, then I can actually make that curvature perfect. So that's the reason why I can't divide this into a finite number of disks, but I can divide it into an infinite number. And if I take the limit as the thickness goes to 0. That's why we're using integration here. So the strategy is I want this guy to become infinitesimal thickness. So it's going to be a real disk, but it does have an infinitesimal thickness. That means it'll have an infinitesimal size, and that means it'll contribute an infinitesimal amount to the center, to the moment of inertia. That's what the di represents. And the integral is because I'm going to add up all of those disks. So this is progressing just like we did for center of mass then. But I need to know what the di equals. So here this is a really useful information already. I know that a disk is half mr squared, but what I'm interested in now is an infinitesimal disk. So I really want di for a disk. I want to make this into a differential version. What does this formula look like when it becomes differential?
MR.
This is the key question. We did this last time with center of mass. So Gabby, you say it's dm. Why do you say dm? It will be different, but why is it differential? Differential means it's basically going to 0 in the limit. Is that really what's happening?
Small, so it's dividing all of them.
Yes.
As you get smaller disks, then it's going to approach 0.
So this is the tricky thing. You want it to be r because you feel like r is the coordinate, so you're kind of anticipating, but r is not going to 0 here, right? What does r represent in this for this disk?
Or is radius.
It's the radius of the disk,
From the
right? So
center.
it's this is here. Is this distance going to 0 for this disk? No, right? So when you turn a formula into a differential form, this is the contribution here is becoming differential, and other things over here are going to be becoming differential as well. They're going to be going to 0. And the mass is the thing that's going to 0. Here's r right here, right? So I should have called this lowercase. So be mad at me for changing, but I need to change this to lowercase because it's going to conflict. I want the radius of the sphere to be r, capital, and the total mass to be big M. So let's say that we just call these, so we don't conflict in the name, we call these lowercase. It is going to be a dm because if the thickness goes to 0, the size is going to 0. And that means the amount of mass on that disk is going to 0 too, right? So it is the end that's going to 0. But the r is not going to 0 because that is just the radius of the disk. And as I make it thinner and thinner and thinner, this radius just stays, is just some finite value. It's just this value. It's not going to 0. Don't be confused by the fact that this point up here, there'll be a very, very tiny disk up here, right? But that's just one disk, right? That's a special disk. I want this formula to work for any of the disks. And all of these disks are getting very thin, so they're all having their n go to 0. But most of them have a larger value for r, right? So this should be our formula here. Somebody have a question?
But, I mean, little r and big r are not the same.
Yeah, they're not the same. So big R is supposed to be the radius of the sphere, and little r is the radius of one of my disks. This little r will be changing. Every disk will have a different value. Okay, so this is the very first substitution that we make, and we say half dm of r squared. So this is, again, we're integrating over all the disks. So the dm is supposed to be the mass of that disk, and the r is supposed to be the radius of that disk. So we're starting to run out of time for finishing this, but the next thing that we do, what is the next thing that I say that we should do from this point forward? We succeeded in substituting di into a more concrete form, but it's still not quite as concrete as we'd like it to be, right? Yeah, I'd like to substitute for dm now. So dm is not really concrete, it's not really in the form of like a coordinate. So I'd like to see if I could re-express dm as something else, like how much mass really is on this disk right here. The way that I do that, do you remember the strategy that we approached for these? Yeah, we use like a density. What is the density of this sphere?
Volume divided by mass.
Yeah, other way around, right?
Mass over volume.
Mass per unit volume is density, right?
Mm-hmm.
And I know that for this, right? Because I know the total mass. Do I know the total volume? Right. So total mass over total volume would look like this. So I do know the density. I have all the parameters that I need for the sphere. If I know the density, then I know like the mass per unit volume, right? That's what the density is. So now I basically, in order to find the mass of this guy, what do I need to know then? I would need to know what the volume of it is, right? So basically, if I know the density, I can take any shape of any volume, multiply it times the density, and that'll give me the mass, as long as things are uniform, which they are here. So basically, I need to know what the volume is. The volume is going to 0. Of course, it is differential because the size of this is going to 0. This would be like the first step that I would take. Like the next substitution. So the next thing that we would need to do is actually figure out what is the volume of that disk. That would be the next substitution we would have to make. Once we do that, it's going to be in the form of different coordinates, and we would be able to continue looking at that. So we've run out of time for today. In my opinion, this is probably the most difficult part what we've done so far. So you could attempt to finish this. One really important thing that you're going to need to know is I drew an example disk here which has a radius I call little r, but I'm going to need to try to label the position of that disk somehow. So a good idea would be to define a new coordinate such as z, where z would be the distance from the middle up to that disk. So we could define a coordinate like that z. That's just something that we introduce into the problem that's going to help make it a little more concrete. But based on what you have up here on the board right now, I'd encourage you to try to finish the problem. Maybe we could revisit this on Wednesday, because we ran out of time. But this is kind of a beginning, and you can see how this is, the strategy is just like center of mass. But it's just, we're adding up something different in this case. Okay, so that's all for class for today. I will send out a comment this afternoon about a shorter homework assignment that'll be for